concept of internal stability. So if you start with a system, now you've got the state space description. Let's look at a time-varying linear system. Then, and suppose that the core system, so the internal system, just looking at the details of the A of t matrix, suppose that this is an exponentially stable system. So the equilibrium at 0 of this, what we call the undriven system, so when u is equal to 0, we say that the system is undriven. So xe is equal to 0 of x dot equals a of tx is exponentially stable. All right, so we're looking at the internal dynamics of the system. And so we've got that condition. We've also got the condition that the way that the input enters the system and the way that you see the system from the output, those matrices are bounded. So B, C, and D are bounded matrix functions. All right, so they're bounded functions of time. Then, under these two conditions, then the system L is bounded input, bounded output. Okay, and the proof of that is fairly, well, the proof of that kind of is just a boundedness argument, which follows from looking at the input-output response from this time-varying system in terms of the weighting pattern matrix. So if you know that this system is exponentially stable and these matrices are bounded as functions of time, then you can establish that the supremum over t of the integral from minus infinity to t of h of t tau u of tau d tau is a bounded function, and that's our condition for bounded input, bounded output stability. Okay. We're in lecture notes 15, page 7. So exponential stability of A of t implies bounded input, bounded output stability of the input-output system.
So that's sufficient but not necessary, right?
It is sufficient, and it's not necessary. So the direction is, if this is true, then we have that the system is bounded input, bounded output stable. But and there are cases of systems where, so for time invariant systems, exponential and asymptotic stability are the same thing. But in the time varying case, you can come up with conditions of asymptotically stable systems which are not bounded input, bounded output stable. So it's not true for all asymptotically stable systems, but what exponential stability of the system does is it gives you kind of a robust stability result that can't be disturbed by bounded inputs. Okay, so this is the direction is from the concept of exponential internally stable to bounded input, bounded output stable. And we went through some of these examples that are in lecture notes 15 last day to show, for time invariant systems, how you can have an unstable system that's still bounded input, bounded output stable. In fact, we saw examples of linear time invariant systems. We diagonalized them, so we put that into what we call diagonal form, or as I said in the email today, modal form. Modal and diagonal form mean the same thing. And you can just by placing the zeros in your B and C matrix, you can make that system have a transfer function which results in a bounded input, bounded output stable system. Right? So bounded input, bounded output stability doesn't necessarily imply exponential stability or asymptotic stability. Right? Okay, so you can see those examples. And we talked about the concept of a hidden mode last day. Hidden either from it's not accessible from the input, or it's not observable from the output. And a couple last points. So I want to pick up at the last topic of stability that we'll cover before moving on to the last unit of the class, which is controllability and observability. We're actually going to introduce both controllability and observability today. But let me just say one thing before, and it's kind of a beware. This is often a point that we have to be careful of. So suppose you have, okay, so last day we talked about stability of linear time invariant systems, and we have the result that a linear time invariant system is exponentially, equivalently, asymptotically stable, so stability of that system is equivalent to the spectrum of the matrix A being in the open left half plane. All right, so that's something that we studied last day. That's a linear time invariant result. Suppose you had a time varying system. So suppose you had a system where your dynamics evolved according to a matrix A of t. But suppose A of t were kind of special, and it had constant eigenvalues. Suppose those eigenvalues were all in the open left half plane. Could you still conclude that the system is exponentially stable? Seems reasonable, right? Is it true, though?
Maybe you can't say like x of t is equal to the matrix exponential.
You can't say that, right? Because now it's a time varying A, right? So we need to have like a state transition matrix. We need to compute that properly. And that's kind of at the heart of it, right? You no longer have the e to the at relationship between the matrix and its the solution to that differential equation. So this is where it's a warning. You have to be careful. So warning. Warning. This result does not, in general, carry through to time-varying systems. Even when the eigenvalues of A of t are all constant and in the open left half plane. And there's here's just a counterexample, or an example which is a counterexample to the system being stable if all the eigenvalues are in the open left half plane. So suppose you had an A of t matrix. So it is a time-varying matrix. It's upper triangular, so you can just observe that the eigenvalues are both -1, but it's got a time-varying component in, which is e to the 2t here. Okay, so if you look at that system, you say, aha, well the eigenvalues are both, they're just the diagonal elements because it's upper triangular. They're both at -1. They're both in the open left half plane. That, that looks, that looks like it would indicate stability. But then we remember that we're not computing e to the at. We don't have that simple relationship anymore. And so if we actually compute the solution to this, and I've done it in the notes for, now we're looking at a system which is x dot is A of tx. It's a two-dimensional system, and we set the initial condition, just to make things simple, at 0, 1. So if we solve this system, it's upper triangular, so this is sort of one of the cases where the state transition matrix is easier to solve. You did an example like this in your homework when we were looking at the computation of state transition matrices. So if we solve first for the second equation here, x2 dot equals -1 x2, we get that for this times x naught, so times that initial condition, we get that x2 of t, everything looks nice there, x2 of t is e to the -t, but now we plug that in, so x1 dot is equal to minus x1 plus e to the 2t times x2 of t. So that's e to the 2t times e to the minus t. And so what we end up with is, let's just write it out on the bottom here. So now this is, so that's e to the t. But what happens here, so I can solve this. This is just like my regular, first order linear equation driven by an input, which is an unbounded e to the t. So I know what the solution looks like. So x1 of t is going to be x1 of 0, which is, or it's going to be, the e to the at, but a is just minus 1 here, times x1 of 0, which is 0, plus the integral from 0 to t of e to the a is minus 1, t minus tau. So that's e to the minus 1, t minus tau, times the input, which is just e of tau, d tau. And this example was chosen so that we can do that integration nicely, and we end up with, that's just, if we solve that and we integrate it, it's e to the t minus e to the minus t over 2, which goes to infinity as t goes to infinity. Okay, so we chose an example where the eigenvalues of a of t are constant and they're in the open left half plane, but it's a time-varying matrix and it's an unstable system. Question?
If all the entries in the matrix are polynomials, say, can I now make the claim that this would have to be exponentially stable?
There are a couple of cases that you can generalize this to. Now, you looked at that and you said, well, it's really the exponential here that's screwing things up, right? So if I made my input polynomial instead of exponential, so it's growing with time, but it's not growing exponentially, is that going to be dampened out by that e to the minus t? And now you have to look at it a case-by-case basis. So the general conclusion is that there do exist some generalizations. Actually, let's talk about the generalizations that we can state, because one of them I think I'd like to prove. It's a kind of nice segue into Lyapunov theory. But in general, you have to do these on a case-by-case basis. So you have to make sure you can see that this is going to decay faster than this grows. But how that comes in.
They're all polynomials when it comes out.
Yeah, but it depends. So if this is a polynomial, is it going to be dampened out by e to the minus t? Yes, in general. But now, so now you'd have a bounded. You'd have to be able to show. So if it's an upper triangular system like this, and this were a polynomial, you'd have to be able to show that it's a bounded input, bounded output. Like that what you're putting in, what we're calling the input here is bounded. Because this part here is exponentially stable, and then yes, you would get a stable system. So there are a couple of cases when the eigenvalues of a of t do allow you to generalize. So I'm just going to call this generalizations for linear time variant systems. And your question is interesting because it would seem to work here for this case where it's an upper triangular matrix and this is a polynomial. But in general, if all the entries are polynomials, we'd have to work it out. And I imagine that in some cases it will, and there may be some cases where it doesn't. We'd have to work it out. But here are some cases that are definitively, you can prove stability. So suppose you had an A of t matrix which was symmetric. So A of t, it's time varying, but it's symmetric. So for any point in time, the A of t is equal to A of t transpose. Okay, so A of t is symmetric. Does anybody know what you know about eigenvalues of symmetric matrices?
Real?
They're all real. The eigenvalues are all real. What about the eigenvectors? They're orthonormal, actually. They're orthogonal when you can write them in an orthonormal way. So just go through the exercise of showing that for a symmetric A of t, its eigenvalues are real and eigenvectors, evex, are orthonormal. So that means that if you were to try to, well, it says a bunch of things now that we know about diagonalization. If it has n eigenvectors and n eigenvectors which are orthonormal. So it's diagonalizable, first of all, because it has n orthonormal eigenvectors. And if we think about the matrix the similarity transform that takes this matrix to its diagonal form, so let's call, I'm going to use the notation that we've introduced from the beginning. So T inverse is a matrix whose columns are the eigenvectors of A of t. Okay, E1 up to En. So that's equal to T inverse times a diagonal matrix. And moreover, we know that this matrix is orthonormal. That tells us that we can define these eigenvectors so that the norm of that matrix is equal to 1. All right. So if this is the case, then we can say that if the eigenvalues of A of t, so we know they're all real, if they're all less than or equal to some negative real number, I'll call that negative mu, where mu is a positive real number, where mu is positive, so negative mu is less than 0, then the system x dot is equal to A of tx has exponentially stable equilibrium at 0. Okay, so we define stability as we did last day in terms of the stability of the origin.
For this, like, are we saying that as soon as like A of t is symmetric, then you're like in case 1, like the diagonalizable case?
No, what we're saying is, yeah, we're saying that. So we're saying that as soon as the matrix is symmetric, then its eigenvalues are real, and its eigenvectors, of which there are n, form an orthonormal set. So that's something that you should just go through and make sure that you see why that's true. But what we're saying here in this case 1 here, is that if we have a symmetric A of t, then if the eigenvalues are all to the left of a negative real number in the complex plane, then the system is exponentially stable around the origin. So that means that, if you plot in the complex plane, and we have this, here's minus mu, then what we're saying is that the eigenvalues, they could be time varying, right? But for any point in time, they're always to the left of that line. Yes?
So that's like the same thing as saying A of t is negative definite, right? Or do you not talk about definiteness for time varying?
Yeah, you can say that. For any point in time, A of t, or for all time, A of t is negative definite. Yeah. But we want it to be robustly negative definite, right? So it has to be less, the real part, actually, why did I do it like that? They all have to be real. That was incorrect. So they're all on the real axis, they're all on the negative real axis, but they're bounded away from 0. So they're less than some negative number. And the way to prove this is quite nice. I think we'll go through the proof. Because the proof, as I said, leads us into the last unit, the last concept of stability, which is, a piece, we'll just do a piece in this course of Lyapunov stability, that for linear systems. All right, let's let's go over here, prove this. So if you have a time-varying system, and you know something about, and it's symmetric, so proof. So this is the proof of generalization case 1. So we have x dot is a of tx, and we know that a of t is equal to a transpose of t. And we also know that the spectrum of A is to the left of minus mu. Okay, so we're going to prove the stability of this in a little bit of an indirect way. I want to prove exponential stability. So I want to show that x of t is bounded below by a decaying exponential, or the norm of x of t is bounded below by a decaying exponential. So I'm going to try to do this by invoking a separate function, which I'm going to use to prove this. Consider a function, and we'll call it v of x. I'm just going to use this function here, which is x transpose x. So this is, we'll see that this is called later a Lyapunov function. And let's take its derivative. So we mean, by taking its derivative, we mean its derivative with respect to time. But when we take its derivative with respect to time, that gives us x dot of tx plus x transpose x dot. But x dot here has a special meaning for us. X dot represents the dynamics of the system. So it's so we have already an understanding of of what x dot is, because we've got a system evolution here. So when I take that derivative, this is actually kind of a special derivative. It's like the total derivative with respect to time. But what I'm doing is I'm plugging in the dynamics wherever I see x dot. So this is x dot transpose. So that's x transpose a transpose of tx plus x transpose and then x dot, which is just a of tx. This is a derivative which we won't spend a lot of time talking about it, but we learn a lot about this in the nonlinear systems course 222. It's called a Lie derivative. L-I-E is pronounced Lie, after a Norwegian mathematician called Marius Sophus Lie, who he worked in calculus and geometry and kind of brought together these concepts of derivatives and dynamics together. It basically just means it's the rate of change of a function along trajectories of the system, because you're plugging in the system dynamics wherever you see x dot. Okay. So we've got this v dot here, and we've computed it. But we know something special about case 1. We know that the system's symmetric. So I can replace A transpose with A and just write this as 2x transpose A of tx. All right, now, but I know something about that quadratic form now, this x transpose A of tx, because I know that the eigenvalues of A are all real and its eigenvectors are orthonormal. So I can in fact write A of t in terms of its diagonal form as A of t is equal to t inverse lambda times t. And I can actually do a little bit more here. So I know that these eigenvectors are orthonormal. I also know, because these eigenvectors are orthonormal, I know that T inverse is equal to T transpose. So that should be part of the exercise. If this matrix, the columns of this matrix are orthonormal, then you have that the inverse of the matrix is just the transpose of the matrix. That just comes out of the fact that this is an orthonormal set. Okay, so that helps us over here, because now we can replace this with, well, what can we do? We can replace A of t, let's just replace A of t with t transpose, lambda of t, tx. And then I can look at that and say, well, if I look at that matrix here, that's just a matrix where I've got, you know, lambda 1 of t, lambda 2 of t, it's just as lambda n of t, so the eigenvalues. And there's some maximum value of those eigenvalues, and there's some minimum value of those eigenvalues. So I can now further simplify this product and say that that is going to be less than or equal to that product where I take, you know, the maximum eigenvalue. I take this matrix here and I replace it with a matrix that just has the maximum eigenvalue along the diagonal. Okay, and because then I can pull that out, that's just that maximum eigenvalue times the identity matrix. So I can rewrite that as less than or equal to 2 times lambda max norm tx squared. But norm tx squared is just equal to norm x squared because of the orthonormal columns of t. So this is just 2 lambda max times norm x squared. Okay, so we have that v dot is less than or equal to this upper bound, and we invoke now this this assumption that whatever lambda max is, it's going to be less than minus mu. That's one of the assumptions, and so this becomes less than or equal to minus 2 mu norm x squared, which is just v of x. All right, so I have it here what I call a differential inequality in this function v. So v dot is less than or equal to minus 2 mu v. If that were equal here, we could just write a solution for what v of x looks like. This is just our x dot is equal to, let's just think of v of x as just being x. X dot is equal to some scalar times x. So we can solve that differential inequality just using the same techniques that we've been familiar with so far, looking at linear time invariant system solutions. And I can replace that with, therefore, from this expression here, I have that v of x of t is going to be less than or equal to, just replacing, you know, we usually use an equality, now that's replaced with an inequality, v at x at time 0, e to the minus 2 mu t. Okay, I've just solved that differential inequality. It's a linear differential inequality, just like a linear time invariant equation. All right, and now I go back and replace, you know, wherever I saw v's, I'm just going to substitute back x's. So that tells me that's norm of x of t squared is less than or equal to norm of x of 0 squared, e to the minus 2 mu t. And now I get the result that I want. X of t, just taking the square root of both sides, is less than or equal to x0, e to the minus mu t. And there's my exponential bound. So it's bounded below by a decaying exponential. So this was a special case in which I could do this because a of t is symmetric, so I can, you know, replace this with a of t, and then I was able to use my known bound. The largest eigenvalue is less than negative mu, where mu is a positive number. Okay, so that therefore I get the exponential stability of the equilibrium at 0. Okay, so that's case one. That's one special case where the eigenvalues of a of t can tell you something about the overall stability of the system. A second special case, so generalizations continued, is case 2. And this case is a little more complicated. So if the real part of A of t is less than or equal to minus lambda, which is less than 0, so lambda is positive, and that's true for all t, that means the real part of the elements of A of t, so you form a matrix whose elements are just the real parts of the elements. And if you also have that the norm of A of t is less than or equal to epsilon, and epsilon has to be small enough, what that means is, epsilon will come out of the proof and it will be related to the size of the elements of A of t, then you can conclude exponential stability of the origin of x dot is equal to A of tx. And I said the proof of this, it's not very enlightening. It's not like the proof of the previous one, but this is kind of maybe a special corner case that is, it's not the easiest thing to analyze or prove, and we just won't do that in the class. Okay, so in general, the sort of lesson to take away from this is a time invariant system. Our test is really looking at the eigenvalues. Or equivalently, as we'll see, we can come up with some Lyapunov stability test. But for time varying systems, you have to be careful. You can't, in general, just look at the eigenvalues unless you have either some general special structure like this, or you can do something, you can go in and look specifically at, for example, if you had all constant eigenvalues that were negative and you had polynomial functions, could you go in and look at that on a case-by-case basis? So case-by-case stability there. Question?
So we call that the Lyapunov function. So is the person that's named after especially interesting or?
Very interesting. So yeah. Lyapunov, and if you take 222, if you take 222 with me, you get a history lesson about Lyapunov. I think Professor Archak gives a little bit of a history lesson about Lyapunov as well. But really a very interesting researcher who was looking at stability of the solar system, and will small perturbations that are being observed in the ellipsoidal paths of planets, will those grow over time and cause the solar system to explode? So this is kind of like 1890s. He was doing his PhD thesis in St. Petersburg. He was a student of Chebyshev. And he was the one who came up with a general way of assessing stability of nonlinear systems. And his journal paper, his PhD thesis was on the general properties of the stability of motion. And at the time, he was, there was kind of a competition between Russia and France about who was going to come up with a solution to the stability thing. And
US wasn't in the running.
well, no, I think everybody was in the running, but the mathematicians in Russia and the mathematicians in France were kind of leading this effort. And it was really hard for him to get his PhD published. There was some kind of competition going on with the French at that time. So he ended up, it ended up being published, like 20 years later in this sort of fairly obscure journal out of the University of Toulouse, not in the main kind of academy, the French Academy of Sciences journal. But it's something that, it was I think it was very insightful even at the time. And then in the 1960s, it was Kalman, Rudy Kalman, who recently died, of the Kalman filter, etc., who really brought that to control, who said, look, this idea of Lyapunov can be incorporated into control design, and it's really that sort of entry point that brought it in, and I think why we use it a lot in control theory today. Yeah, that's my abridged version of Lyapunov. Yeah, okay, so let's actually talk a little bit about Lyapunov for linear systems. And we're going to focus on the time invariant case, even though this theory, Lyapunov stability, is more general. It applies to time varying systems. In fact, in the Kalientosor textbook, you have the full time varying theorem. And as I said, it applies generally for nonlinear systems as well. It's as I think I've told you twice now, it's one of the most portable techniques to come out of control theory to be used in other areas. Question?
For LTV systems, if any of the eigenvalues are positive, is it guaranteed to be unstable?
I think so. I think you can fairly easily prove that by just looking at, you have to be careful because are they positive for a point in time, or are they, basically negative and then they go positive for a point and then they go negative again because the eigenvalues are changing with time. So, but if there's one eigenvalue that's positive for all time, then I'm pretty sure you can fairly easily prove that the system is unstable. Okay, so let's just, in the last few minutes about stability, let us focus on an equivalent test for exponential stability of linear time invariant systems. All right, so we already have a test which we went through last day, which is the test of the eigenvalues. There's an equivalent test, and this equivalent test turns out to be actually incredibly useful. Maybe not just for direct proofs of stability for linear time invariant systems, but more as a technique for proving stability of more general systems. Perhaps you have a nonlinear system and you do a Jacobian linearization, so you look at that linear component. Lyapunov theory allows you to prove stability about the nonlinear system locally, based on the stability of the linearization. And so things like that. So it is something that, coupled with different kinds of systems, is a very powerful technique. Okay, so let's call this an equivalent test for stability of x dot is equal to ax, the linear time invariant case. And so the theorem goes as follows. Suppose that you have, all right, so you've got your linear time invariant system.
And the stability we're talking about is exponential stability, right?
It's exponential stability. For exponential stability of x dot is equal to ax, for the equilibrium at the origin. Okay, so the theorem is as follows. Consider the following equation. And this is called a Lyapunov equation. Lyapunov equation. Okay, so by definition, what is a Lyapunov equation? It's the following. A transpose P plus PA is equal to minus Q, where P and Q are positive definite matrices. So we write that as follows. Where Q is equal to Q transpose, and it's positive definite. Okay, so, well, actually, no, let's write it the way I have it in the notes, because there's different variants of this theorem. So first of all, we'll just say that P and Q are n by n matrices. A is an n by n matrix from the system. Then the system, so the equilibrium at 0 of our system x dot is equal to ax, is exponentially stable. ES again is exponentially stable if and only if the following condition holds for that Lyapunov equation. If and only if for all Q, positive definite, symmetric, there exists a positive definite symmetric matrix P that solves that Lyapunov equation. The Lyapunov equation has a unique positive definite solution, P is equal to P symmetric solution, P equals P transpose is greater than 0. This theorem is actually more general. I mean, you can actually derive a whole bunch of equivalences between, for all Q, there's a positive definite solution, or there exists a matrix Q such there is a positive definite solution. But we're presenting kind of the more, maybe the most popular version today. And we're not going to prove the if and only if. We're only going to prove the one direction, which is sort of useful to us from this kind of stemming from what we just did in terms of introducing a Lyapunov function for that previous example.
But the way that you wrote it there, are you saying that the symmetry of Q matrix implies that equation that's the unique solution? Like, I don't know, it seems like there's two parts of this kind of.
So the system is exponentially stable if and only if, for all matrices Q, positive definite symmetric, the Lyapunov equation has a unique solution, P, which is positive definite symmetric. Okay, so we're going to prove the if direction. So we're going to prove this direction here. And we're going to do it through invoking, like we did in that last example, a Lyapunov equation. Consider the following function. V of x, instead of being x transpose ix, where I is the identity, which is the one that we used in our previous example, we're going to use the following, x transpose px. Consider the following function, which we call Lyapunov function candidate. Okay, so I'm taking that matrix P, which is by assumption of my theorem, because I'm assuming this is true, and I want to prove exponential stability of the origin. I'm assuming that P is a positive definite symmetric matrix. So x transpose px is what we call a positive definite function. It's always positive except at x is equal to 0. Okay, so now we're assuming that this is true. So for all positive definite symmetric Q, there exists this solution P. So we took that solution P and we, for some positive definite Q, and we plugged it in to form this function V of x. Okay, so we've got a function Q. So we were given that Q. And we chose P to be the, right, let's write it out just to be clear, that P here was the solution to the Lyapunov equation. Okay, now let's follow what we just did in the previous example. Let's take V dot of x. Okay, so now sort of the same thing we did before, but now this is x dot transpose px plus x transpose px dot. And wherever I see x dot, I'm going to plug in the dynamics of the system, which are just ax. So this is x transpose A transpose px plus x transpose PAX. And then I'm going to factor out x transpose in the front and x in the back to give me x transpose A transpose P plus PA times x. And that's, by assumption of that P solves this equation, that's just minus x transpose QX. All right, so I've got two key equations here. I considered a function. I started with a function, x transpose px, where for a given q, p solves the Lyapunov equation. And then I computed v dot, which is this function here. Okay, so I've got v of x is x transpose px, and v dot of x is minus x transpose qx. And I know that both p and q are positive definite symmetric matrices. All right, so based on what we did here, we can sort of derive similar bounds for x transpose for these quadratic forms, x transpose px and x transpose qx. So we know, and I won't sort of repeat the analysis that went into this, but we know that lambda min, the smallest eigenvalue of p, times norm x squared is less than or equal to x transpose px, which is less than or equal to lambda max of p times norm x squared. Okay, just using the same analysis that we did in the previous example. And then similarly, I know that lambda min of q times norm x squared is less than or equal to x transpose qx, which is less than or equal to lambda max of q norm x squared. So this notation means, you know, in all of this, the maximum eigenvalue of q, minimum eigenvalue of p, etc. So now we want to be able to establish exponential stability of x of t. So let's sort of look at what, we've got four inequalities here that are going to help us. We've got that v of x is x transpose px, and we've got v dot of x is minus x transpose qx. So let's start with, let's go back to our v dot of x, which is minus x transpose qx. And let's use this bound here. So I know that x transpose qx is greater than or equal to lambda min of q norm x squared. I also know that all of these lambdas are positive, right? Because that's what I assumed about p and q. So I know that negative x transpose, so remember to maintain the negative across the inequality sign. So this is less than or equal to negative lambda min of q times norm x squared. Okay, because when I put a negative, I flip the direction of the inequality. Okay, but going back to where I was before, I want to get a differential inequality in terms of v dot and v, but I still want to maintain that bound. So I'm going to replace negative norm x squared. So I know that negative norm x squared is less than or equal to negative, let's be careful here. So this is v of x. So that's less than or equal to negative v of x over lambda max of p. All right, so now I'm using this inequality here. And so I can plug that in here and still maintain that. Therefore, v dot of x is going to be less than or equal to negative lambda min of q over lambda max of p times v of x. And now I just solve that. I just integrate it like I did in the previous example. So integrate, and you get that v of x of t is less than or equal to v of x at time 0, e to the minus lambda min of q over lambda max of p to the for t greater than or equal to 0. Okay, but eventually we want that back in terms of x, because we want to establish, for exponential stability, we want to establish a bound on norm x. So now I have to maintain that inequality, so now I'm going to use this one here, over here, on the left-hand side, lambda min of p norm x squared is less than or equal to v of x 0, so now finally I'm going to use this one again. Lambda max of p, and it's at x 0, so this is lambda max of p times norm of x 0 squared, because this holds for all x of t, including x at time 0, times, and that is decaying exponent, e to the minus lambda min of q over lambda max of p. Okay, and now you just take the square root of both sides and divide through by lambda min of p. So that you get norm of x, and I'll just put the t back in, it was always there, I just wasn't writing it, is less than or equal to the square root of lambda max of p over lambda min of p, e to the square root of this, well actually let's put x 0, norm x 0, and then e to the, so we divide it by 2, so e to the minus 1/2 lambda min of q over lambda max of p. Okay, so now we've established exponential stability. Yep.
With the second last line, which piece of these equations did you drew the arrow, but which one did you use?
So this piece, let's use color here. So this piece here, this inequality I used for the first time, and I used it for this piece here, and then to replace v of x 0, I use this inequality for the second time. So that green one I used to replace this one here. All right, so now we have exponential stability. Exponential stability of xe is equal to 0 for x dot is equal to 0. Okay, so we're going to actually leave it at that. There's a lot more to say about Lyapunov, and it will all be treated in a lot of detail in the nonlinear systems course. But something, you've just been kind of teased here, because you've been shown a technique for assessing stability which draws on a function that was kind of external to everything. We had this function v of x, and we're using properties of v and its total derivative with respect to time, something that we've just defined now as the Lie derivative. But we're using properties of v and v dot to understand how the system is behaving. And so the theory of Lyapunov is really based on coming up with appropriate functions v that, when you take their derivative, they allow you to say something about the stability of the system. So how are they linked? Like, where did the dynamics come in? The dynamics came in when we took the derivative, because this x dot is actually the dynamics of the system. And so what v dot means, and this is what you learn very carefully in nonlinear systems, what v dot means is the rate of change of the function v along trajectories of the system. So if you have functions v which look like bowls, like they're bowls, like our x transpose px is a positive definite function. It looks like a bowl, or maybe an ellipsoidal bowl, depending on what the matrix P looks like. If your trajectories are such that they're always moving in a direction of decreasing v, it means they're moving towards the origin, because v is 0 at the origin and nowhere else. And that's really what's happening here. But it's a very general theory that we can apply in many different cases. Okay, so what we've presented here is the specialized case for linear systems. And this holds for linear time varying systems too. Namely, if you replace the A's and the P's and the Q's with time varying, their time varying matrices, the theory still holds. We just presented it kind of a snapshot in the case for the linear time invariant case. So this is an equivalent test to the test we have for the eigenvalues. If all of the eigenvalues of A are in the open left half plane, then for all Q positive definite, there exists a P positive definite which solves the Lyapunov equation. So that's an if and only if as well.
So which particular times would we want to do this seemingly more complicated check than just the eigenvalues?
You want to do this when, you typically don't do this when you have a matrix A where you can just look at the eigenvalues. You want to do this in cases where you're doing something more complicated than just looking at the eigenvalues of A. Namely, one way that you've kind of experienced this already in 221A, you have a nonlinear system, let's suppose it's time invariant, x dot is equal to f of x. You perform a Jacobian linearization, and you can write this now as x dot is equal to, I won't use j, because that's what we've been using for our Jordan form. Let's use a x plus g of x. So this is the Jacobian linearization of f, Jacobian of f, around some point, say x equals 0 is often a point we're interested in, plus g of x. And what's g of x? It's the leftover things. It's the higher order terms. So formally, it's the difference between f and ax. So it's f minus ax. So what you can use now is you can construct a Lyapunov function which is just where p and q are the same here, just for this matrix A. You can pretend right now that this is a linear system. And you can show with this theorem, or a slight extension of this theorem, that you can prove local stability of this nonlinear system, meaning it's sort of around equilibrium, it behaves in a stable way, it converges to the equilibrium if it's exponentially stable, if the eigenvalues of A are in the open left half plane. And kind of the more nonlinear G becomes, the smaller the locality of that region of stability is. So where we typically use this theorem is not just testing stability. If all we have to do is test stability, usually the easiest thing to do is to just look at the eigenvalues. Not always. I mean, this can actually be easier than looking at the eigenvalues. It's for all matrices Q. So choose Q to be the identity and solve this equation. That may be easier than computing the eigenvalues of the matrix A. But often we use it more as a, let's call it a theorem-proving machine for more complex systems. And this is really like the topic of one of the key topics in nonlinear systems that's taught next semester. Question?
I was just wondering, are there any geometric intuitions behind this equation that don't need to refer to the dynamics of the system?
So, just this equation here. Geometric interpretations that don't link to the dynamics of the system. There's a few things that come to mind to answer your question, but they're not really answers to your question. So this is, we can make this equivalent to an equation you've seen before, the Riccati equation. You can sort of see a little bit of the structure of the Riccati equation there. And that's not, that there's actually a formalism that we can connect those to. But I think the answer is yes, that equation has special structure. But how we're using it here, it's necessary to link in the dynamics of the system, because the dynamics of the system describe, it's how A is affecting the evolution of a differential equation that's important when it comes to stability. So I would say yes, there are, but to go into that in more detail requires more analysis. Okay, so let's spend the last 20 minutes of today's class going on to the next unit, which is controllability and observability and control design. So this is the last unit of the course. And we're going to introduce it by kind of going back to our linear system. linear time varying system. We always, if you've noticed in this course, we're kind of following a pattern. We develop a theory for the more general case, the linear time varying case. And we develop the theory, and then we specialize it to the linear time invariant case, which is usually the case where you can actually do some computation. So this is the topic of lecture note 16. I think you all got that. Does anybody need a lecture note 16? Okay, I only have 2 left. There might be a couple of others floating around the room. There's some in the front. Controllability and observability. You've heard me use the term observable before, observable through the output. We even mentioned that a little bit earlier in today's lecture. So let's think right now about where we are. Let's go back to our general time varying linear system, and we'll actually generalize this. You know, controllability and observability are not specific to linear systems. They hold for nonlinear systems as well. But even earlier in today's lecture, when we were talking about this time invariant case, the time invariant version of this where we computed the transfer function, we were talking about cases where even though there was sort of unstable behavior in the internal dynamics of the system, that behavior was not affected by the input. And or both, that unstable behavior was not seen at the output. So that kind of depends on how the matrices B and C interact with the matrix A. D is kind of our, you know, it's like our algebraic piece. It's our direct coupling of input to output. So, you know, often, and you've seen this already in our examples, we kind of said let D be 0. We often do that because kind of where the action is, you know, the way the input affects the state and the way the output is read from the state. This is kind of like a direct coupling where we just take the input and we do some algebraic manipulations on it and put that in the output. Okay, so controllability basically refers to the ability to use the input to affect the dynamics of the system, to affect how X of t behaves. And observability refers to the ability to see the behavior of the internal state through the output equation. So this is like a window. C is like a window into the state. And U is like a filter or some kind of mask or something that can affect the way that you apply, the way the input couples in through the state dynamics. So as I said, these concepts of controllability and observability are more general. They don't just apply to linear systems. We actually introduce them and go back to our old friend, which is our tuple, our 5-tuple of a dynamic system that has a state space, an input and output space, state transition function, and readout map. And that's you know, a dynamic system representation. Then we'll introduce a few concepts which are general for these systems and then which will specialize to the linear time varying and then the linear time invariant case. So we say that the input function, so remember our notation, the input function U between some initial time and some final time, so that's a function. It steers x0, so this is the definition of steers, x0 at time t0 to a state x1 at time t1 if, basically is what it says, if the state at time t1 is equal to the state transition function resulting at time t1 if we started at time t0 at state x0 and applied that input u between t0 and t1 between that time interval. Okay, so steers basically means that you get the input allows you to get from an initial state x0 to a final state x1 in that time interval from t0 to t1, exactly. Okay, so that's the definition of steers. And then we define controllability in terms of the ability to steer a system, or to steer the state of the system. So I'm going to call this dynamic system D. And we say that D is controllable on the time interval t0 to t1 if for all pairs x0 and x1, and that belongs in the state space or whatever, 2 copies of the state space, there exists an input u between t0 and t1, and that's a valid input, so it belongs to our set of input functions, which steers x0 at time t0 to x1 at time t1. Okay, so controllability means that, or it's sort of likened to, if you take any pair of states, here's a state and here's a state, let's call this one my initial and this one my final, then the system is controllable if there exists an input that takes me from this initial state at time t0 to this final state at time t1. Or if I pick these 2 states or these 2 states. So I can get anywhere, from anywhere to anywhere in my state space using a valid input function. So that's what we mean by controllable. And often we call that completely controllable because we can control from anywhere to anywhere in the state space. Okay, so now we can relate controllability back to the state transition function. So if you have a dynamic system D with a state transition function, we'll call this a proposition now after that definition. D is controllable on the time interval t0 to t1. It's very important that we talk about controllability on a time interval for time-varying systems in general. If and only if the state transition function is a surjective function. So that means that the state transition function, it's got many arguments, but what we're saying is the state transition function viewed as a map from the input to the final state is surjective. If for all x0, the function s at time t1, given we started at time t0 at state x0, using the input u, so I'm going to put my dot there. It's a little bit different than we have in the notes. So this is a function which takes u to x1. It's a function which takes u to x1 if that function is surjective. Okay, meaning that we can cover, for all x0, we can cover the whole state space with an input, with some, function from our domain, which is the input space. Okay, so this is really, it's a proposition, but it really just follows from the definition that if we want to talk about the ability to go from any initial state to any final state using an input, we better have that for all initial states, the map, this map, which is a function from u to the state space, is surjective. Okay, so that's exactly what that's saying. There exists an input that takes you anywhere in the state space for any initial state. So a couple of loops to look at now. We're going to be defining controllability and observability, but we're going to be quickly applying these concepts to the design of controllers for the system. And we've already seen some feedback loops, and we've already seen some control structures, namely when we studied the linear quadratic regulator. But let's do a little bit of an aside from controllability as an example of controllability. Suppose you had, let's call this feedback and controllability. And this is really some examples of controllability and how it's preserved under feedback. So suppose you had a system, and let's just preserve our notation. I have a dynamic system D. I'm going to look at it from an input-output point of view, so that there is some initial state, but here's my input-output point of view from u to y. And I take that state, so I'm assuming that I can measure that state, and I feed it back through some function, some algebraic function. We call that a memoryless function because it doesn't have any dynamics in it. And I'll just use negative feedback. And like we've been doing, I'll call that auxiliary input v. So I have a new input to the system. Okay, so I'm going to call this system from V to Y. So I had my original system D, and then I'm going to call this new system D sub S for state feedback. And this is just an algebraic function. It's like our matrix K that we computed for the LQR, but it could be a nonlinear function. So the only thing that I am interested in here is that it's a memoryless. It doesn't have any dynamics. It's maybe algebraic function. It assumes that we have access to the state, though. And so here, U as an input at time t is equal to V at t minus this Fs of x of t. So that's one feedback loop that we've been interested in, and we will be interested in. And then another one we'll call output feedback. And I think by its name you can guess what I'm going to write. It's just instead of taking the state, we're going to take the output. I'll feed it back through some memoryless output function we'll call Fout, and that gets fed back, and it gets subtracted from some auxiliary input V. Okay, and this one from V to Y is a new system. So it started with D. This one we're going to call D out for this closed loop system under output feedback. And so here the difference is that U of t is equal to V of t minus F out of x, or F out of Y of t. So there's a nice result that we can prove now with just what we have in terms of a definition of controllability, which is that if D is controllable, so let's call this a theorem, and basically the theorem, and I'm going to state it first, is that controllability is preserved under both state and output feedback. Okay, so that's what we say in words, but maybe a little more formally, the theorem, so let's put that in brackets, but let's just write it. So D is controllable. So our original system, before we added any feedback, D, is controllable on the time interval t0 to t1 is equivalent to saying that ds is controllable. So the theorem works both ways. So ds is controllable and d is controllable. And similarly for the output feedback case, d out is controllable on t0 to t1. Now this theorem is fairly straightforward to prove. Let's look at the intuition as to why it's true, and then you'll be able to see why the proofs work. So what does it mean to be controllable? It means for D to be controllable, it means that for any initial state, any final state pair, there exists an input which will take you from that initial state to that final state. So if D is controllable, that's, if you know that D is controllable, I know that there exists an input which will take me to the final state I want to get to from any initial state. Okay, well let's look at this feedback loop then. If there exists such an input, then in this feedback loop, all I have to do is compute V from U. And then I have the fact that there existed such an input U to take me to any final state tells me that I just take that input U, so I'm going to rewrite this as V of t is equal to U of t plus Fs of x of t, and say the existence of such an input U to make D controllable automatically tells me by this equation that there exists an input V to make the whole closed loop system controllable, because I just take the U that I had before and I add to it this map operating on X. And similarly for the output function case. If D is controllable, then that means there exists an input U to take me to any final state, and the output is just an algebraic function of the state. It's the readout map operating on the state. So the existence of a function U tells me, well, I can automatically compute the V from the U and my knowledge of Y and this output map. So, you know, Fs and Fout are assumed to be known maps. And so we can always just trade off, we can always go back and forth between U and V here. And so the controllability, the ability to control the system through U means that, you know, because this equation is known, we can just as easily control the system through V. And vice versa, right? If this feedback system ds is controllable, that means there exists a V to get from any initial state to any final state. So just compute the U through this equation and you get controllability of the inner system. So the proof that I've given in the notes is basically, you know, writing up just a little more formally what I said in words. But the crux of the matter is that controllability is preserved under state. Well, okay, in this case we've looked at memoryless state. Memoryless state and output feedback, just because of the fact that, you know, we can write down these equations and Fs and Fout are known maps.
For output feedback, have you studied the case that output is not fully observed? That the state is not fully observed by the output?
It's fine because we're still considering the ability to control a state here. So regardless of whether, you know, that's observed or not, where the fact that either this is controllable or this is controllable says something about the state. Since these are memoryless functions, the state variables, the actual number of state variables and their definitions don't change.
Wait, but what if I just said C and D equal to 0? Then it seems like that should...
Yeah, okay, so I skipped something which is called well-posedness. You have to assume that these, you know, that the feedback maps are well-posed. So we'll come back to this next class, but in its basic sort of standard form, where we have, you know, a dynamic system where we've got some kind of readout map, some kind of way the input goes in. If under its general form, which we'll define as well posed at the beginning of next day's class, we can liken these two concepts of controllability. You know, even if B is 0, then you're not going to get controllability of your original system anyway, right? So you have some, you know, you have some basic ability to control the system, which comes through the assumption of the theorem. So one last, let's end today's class by just defining observability. Okay, so we defined what it means to be controllable. Let's look at that same dynamic system, and let's end today's class, and we'll pick up on this and well-posedness on Thursday's class. But we say the system is controllable if there exists an input that steers any initial state to any final state. We define the concept of observability. So D is